Thank you. So, thank you for the introduction, and I would like to thank the organizers for the opportunity to give this talk today. It is the third one about the mathematical treatment of superoscillations, and I will explain you something more about some works which were originated from discussions that we had with Yakir. I liked the description of Eli Cohen this morning about the gifts that Yakir gave to us, and I consider the mathematical treatment of superoscillations one of the gifts that Yakir gave to us. So thank you, and in order to celebrate the birthday, I have a virtual cake. This is the superoscillations cake. That was the cake of the social dinner in Cetraro 2019. And we will have another one next year in June in Cetraro. So happy birthday, Yakir. So as I was saying, this is the third lecture on the mathematical treatment on superoscillations. I will try, I'll do my best, to make it as accessible as possible. So I will repeat something that has been already explained yesterday by Daniele Struppa and Fabrizio Colombo. And in fact, I will repeat some motivating examples and tools. For example, I will repeat something about infinite order differential operators that will appear almost everywhere during this talk, about the spaces of holomorphic functions on which these operators are acting in a natural way. Then I will move to new methods to generate superoscillating functions. In particular, I will explain, this is the focus of my talk, superoscillating functions in several variables. At the end, I will explain something which took a completely different direction. Namely, we proved some results in a framework which is non-related to physics, and it is the, well, at least we don't know yet, it is the framework of the so-called hyperholomorphic functions, namely functions which are analytic, but in some hypercomplex algebras. I will explain towards the end of my talk. The prototypical example of a superoscillating function, better to say superoscillating sequence, is this one. You met already this sequence yesterday in the talks of Daniele and Fabrizio. We can start from this expression here. It's very simple. It can be rewritten as a finite linear combination of exponentials whose frequencies are bounded by 1, and they have suitable coefficients in front. The coefficients are described here. They can easily be obtained from this definition with easy manipulation, let's say. You will notice that when A is a real number which is taken greater than 1, they oscillate. So they take values which oscillate between plus and minus, values which are in modulus getting larger and larger. It is known that in the limit, this sequence tends to this exponential, e to the IAX. So the reason to call the sequence superoscillating is absolutely clear. We start from exponentials whose frequencies are bounded by 1, but in the limit, we get a frequency which can be arbitrarily large. Now, Aronoff original questions for us, at least this is our reformulation of your questions, were, yes?
So I admit I'm an outsider to this concept. But if you have a finite and very large but finite, do I think correctly that what happens is that over a finite range of the real axis you have very fast oscillations, but then as you get out of that range,
it exponentially grows.
It exponentially goes?
Yes.
All the way to infinity?
Yes.
To x equal plus and minus infinity?
Indeed.
I see. So in the cases that were discussed yesterday, for example, in the harmonic oscillator wave functions, those would be wave functions which diverge at the points at which the potential gets very large.
Yes, in general, yes. So in the limit, the function is the exponential. It has tails, which are exponentially growing, and it has fast oscillation in a certain region. If you fix n, the region where it oscillates is, roughly speaking, plus and minus the square root of n.
And is the function normalizable? Or it's not? Because
No, in general, it is not. So, as I was saying, our reformulation of Aronoff original problems were, first of all, to study the evolution of these superoscillating sequences, for example, under the Schrödinger equation or under other field equation. Then another question was, how large is the class of superoscillating functions? Because we have been discussing a lot this prototypical example. But the first natural question is, can you write other examples of superoscillating functions? Then the question, which has been treated yesterday in a rather, well, complete way, complete according to the results that we have so far, is to study the persistence of the superoscillations under different potentials, using, for example, Schrödinger equation. And the question I will treat today, namely how to extend the notion of superoscillations to the case of several variables. And you will see along the way that this is not an artificial question for the sake of generalization. You will see that the several variables case naturally appear while studying the evolution. So, as I was saying, today I will treat with some detail the case of several variables, and as a byproduct of my discussion, I will enlarge the class of superoscillating functions. So, first of all, let me repeat something which has already been explained yesterday by Fabrizio. So, the evolution in the case of the free particle. So, I consider this Cauchy problem in which the initial datum is one of these functions, Fn. I will denote, just to ease the notation, Fn of x without writing explicitly the a, although it depends on a. As Fabrizio was showing yesterday, the time evolution of this function is given by this expression here. So this is the evolution of the Fn. And it can be explicitly computed, as you see. So to see if superoscillations persist in time, we have to compute the limit of this sequence. Assume that we have computed the limit. It's a function psi of x and t. The question is it still a superoscillating function? Namely, it is true that in the limit here we have a function that has a frequency that is larger than the frequencies that we had as an input. We shall see that the answer is yes to this problem. And to prove that the answer is positive, first of all, we wrote in a different way this function psi n that has been computed a moment ago. Indeed, the claim is that this function can be written by applying an infinite order differential operator to the original function fn of x. What is the proof of this fact? This is a rather peculiar operator because infinite order differential operators do not appear normally if one considers differential equations which are more classical, but they appear here naturally while studying the evolution. How do they appear? Well, simply take this expression read here and rewrite it as series. And so, in the function psi of n, take this part and rewrite the expression using the series expansion. Then, one observes that this term here in reality can be obtained by taking the derivative of order 2m of this exponential function in the space variable x. So this term can be substituted by these derivatives. Now put together this with this, and you see the infinite order differential operator appearing here in front of this function that is nothing but our original input superoscillating function. Now, our goal was to compute the limit of the evolution of the functions fn, namely the limit of the functions psi n. That amounts to compute this limit. Okay, formally, if one could exchange the operator of infinite order that I have denoted here by curly u with the limit, then it will be easy because we know that this is convergent to the exponential function e to the iax, and it will be rather easy to compute the result. But as a mathematician, I cannot accept the idea of exchanging the limit with an infinite order differential operator. This is not possible. Well, go back to the class of calculus. When you have a limit of a function in two variables, you cannot simply compute the limit by taking the limit in one variable and then in the second variable and then in the other way around. And you cannot, in general, obtain the same result. So we know that it is not possible from the class of calculus. When this is possible? It is possible when the operator, in this case, the operator curly u, acts continuously on a certain space of functions. Because at that point, if it acts continuously, to compute this limit or to apply the operator u to the limit is going to be the same thing. So we have to guarantee the continuity of this infinite order differential operator on a suitable space of functions. At the moment, let me put on the side this problem, bearing in mind that we have a problem, and let us assume that we can exchange the limit with the operator curly u. So since we know the limit of the sequence of the fn, well, it is sufficient to apply the operator curly u to this function, namely to compute this expression. And with some computations, one can show that this is the limit function. it is the product of two exponentials. And you see, as I was suggesting at the beginning, that you have a function in two variables here. In both the variables, the function is superoscillating. So from this example, the formal solution, it's formal because at the moment I don't know if I can exchange the limit with the operator. The formal solution gives a function in two variables. And they are both, the two functions that I'm multiplying, they are both superoscillating. This opens the way to construct a larger class of superoscillating functions using PDEs. Why? Well, we were computing the limit of this sequence. We got this one. But if we set x equals 0, it is like if we are computing the limit of this new sequence in which we have the coefficients that we had in our original sequence, but here the frequencies are squared. And what we proved is that in the limit, here we get minus a squared times t. So this is a brand new superoscillating sequence. And it is superoscillating because, of course, the frequencies are bounded by 1, but the limit function has frequency a squared. And a is, in general, larger than 1. So back to the operator curly U. The infinite order differential operators act in a natural way on spaces of analytic functions over the complex numbers. So the first thing we have to do is to replace the real variable by a complex variable z. And then we work in the complex case, and then we can go back to the real case. It is pretty much what we do when we are solving equations. Although we start with an equation that we want to solve over the real numbers, it is necessary to work over the complex numbers and then to pick the real solutions, if any. So this is just to create an analogy to suggest that it is necessary to go over the complex numbers. So our operator, if we formally substitute x by z, which is complex, the operator curly u becomes this one. Here in front, we have this expression that was originated in this way in the case of the free particle. But in general, we may consider operators which have some functions in the variables t and z, of course, satisfying some suitable hypotheses in order to be considered. The action of these infinite order differential operators, as I was explaining, is well defined on spaces of holomorphic functions satisfying some growth conditions. The space we will need in the sequel is the space denoted by A1. It is what? It contains holomorphic functions, holomorphic, analytic if you prefer, in the whole complex plane. So they can be expanded in power series, and the series is convergent in the full complex plane. And a function that belongs to A1 is such that there exist two positive constants, A and B, such that f is bounded in modulus by the constant A times an exponential which has B in front of modulus of Z. And this is true for all the complex numbers Z. In general, one could consider here a P where one puts the power P on the modulus of Z. And one can consider such spaces AP for any choice of the natural number P. These spaces are Banach spaces with respect to a suitable topology. Which one? Fix a positive number B, the one that you like. Now, if you imagine to multiply the modulus of f of z times e to the minus b modulus of z, you obtain a quantity which is bounded by a, so it's finite. So basically, for any fixed b, we introduce the set a1b of entire functions such that the supremum of this quantity is bounded. And we know that it is bounded if a function is in A1. Call this number norm f1b. So each of these spaces is a Banach space. And this topology can be used to describe the convergence in the space. And specifically, a sequence f sub j is convergent to f in A1 if and only if you can find a positive real number b such that all the elements of the sequence and the limit belong to A1b, and their different goes to 0 in norm 1b. It seems rather complicated to treat functions, well, to decide if a function is in A1 in the first place, and then how to deal with the topology. We have two results. The first characterizes the fact that a function belongs to A1. It's easy. Write it in power series expansion. The function belongs to A1 if and only if you can find two numbers, C and B, such that the coefficients are bounded by this expression, where gamma denotes the classic Euler gamma. Similar result for AP. It is sufficient to divide J by P. Another good news is a result that allows to decode what it means to have convergence in A1. From the practical point of view, it is enough for any B to find two constants such that this inequality is satisfied for any B in the space A1B. So with these two results and variations of these two results, all of them turn around around the Cauchy formula, and this is why we need the complex case, allow to say that indeed our original superoscillating sequence belongs to A1. This is the first good news. And the second proposition allows to prove that the operator curly U acts continuously on the space A1. So the formal limit that we have computed earlier, it's in fact a rigorous calculation, because the operator can be exchanged with the limit. So up to now, we have been considering a specific superoscillating sequence. We found another superoscillating sequence. We would like to enlarge the class of superoscillating sequences. But first of all, what does it mean to have a superoscillating sequence? This is the first question to be answered. So first of all, we will call the generalized Fourier sequence a sequence of this form, in which we have a linear combination, which is finite, of exponentials, which have frequencies which are bounded by 1 or a certain real number k0 that you pick, and they have some coefficients in front. Well, at the beginning, to speak about a generalized Fourier sequence, we don't need any bound on the frequencies. They are simply real-valued functions. Example of such a Fourier sequence is the traditional Fourier expansion. Then, if we would like to say that a generalized Fourier sequence is superoscillating, then we have to require that the frequencies are bounded by a certain real number, say 1, and there exists a compact subset of R, which we will call superoscillation set, on which Fn converges uniformly to an exponential function of the form e to the I g of A. It is not necessarily A, it is a function of A times x, where g is at least a continuous function of A, it's real valued, and it is in modulus larger than 1. Such a sequence will be called superoscillating. Please.
So this n is finite, right?
Yes, at the beginning here, the linear combination is finite. Then, in the limit, if it converges uniformly to such a function where g of A is in modulus larger than 1, then we say that it is superoscillating.
So if n is finite, the function f, little fn, is finite for every x, right?
Yes, if you fix, yes.
A fixed n is finite.
Yes.
So it oscillates very fast, and then it goes exponentially.
Yes.
And then it saturates.
And then it goes exponentially.
Yeah, but it should saturate, shouldn't it? Because it cannot diverge.
But you have exponentials here.
Yes, but they're oscillating.
Yes. But when x tends to infinity, it's an exponential.
Why? If n is finite, then it seems to me this sum must be finite. No, it's
Yes,
not.
but it depends what you are sending to infinity.
Yeah, that's what.
Yes.
I'm talking about finite n.
Yes. Of course, the classical Fourier expansion is not superoscillating because the frequencies are not bounded by any real number. Okay. Now, earlier we met this type of sequence where p was 2. So we had the square of the frequencies. Natural question, what about if we put a p here? Would this be superoscillating? A natural guess would be that it tends to e to the I a to the power p t. And indeed, this is not just a guess, but this is what happens. And how to prove that? One can consider the Cauchy problem for this, let me call it, modified Schrödinger equation, where here we put the p derivative. One can compute the solution psi n to this Cauchy problem, in which the initial datum is the classical superoscillating sequence, the prototypical one. This is the function psi n. And again, when we compute the limit, we can show that it is the product of two exponentials. And the convergence is uniform on every compact subset of R. Now, we cannot say that this is necessarily superoscillating because it will depend on the parity of P. The oscillations may be damped when n is odd. When P is even, then it is true that we have superoscillations. So indeed, we obtain what I was already predicting. So this power P goes here in this part of the exponent. And in this case, the infinite order differential operators are of this form. Now, we pass from a to a squared to a to the power p. Is it possible to consider something even more general? The answer is yes. Instead of taking just the p derivative here, one may take polynomials in this derivative. We can be brave. We can take series in this derivative, where, of course, the function, the holomorphic function, which is the symbol, must have some suitable properties in order that our procedure will apply. So in general, we can consider this equation associated with a Cauchy problem in which the input, is the original superoscillating function, the datum, I mean. One may prove that the solution to this Cauchy problem is this sequence of functions where the exponential here has the presence of the analytic function capital G appearing. And so in the limit, we obtain the product of these two exponentials. So the treatment is very general, and as you see, it opens the way to create a really large set of superoscillating functions. Sorry, let me go back. If you take z equal 0, you evaluate at 0, it's clearly visible that you start with an input function which may have frequencies which are bounded, and in the limit, if this one is larger than the largest frequency in the original input function, then you get a new family of superoscillating functions. What I have explained so far appeared in a series of papers in collaboration with Yakir Aronov, Fabrizio Colombo, Daniele Struppa, and Jeff Tollaksen. This is the oldest one, the first paper that we wrote together, and these are two follow-up papers which appear both in Journal de Mathématiques Pure and Appliquée. Is that the only method to generate new classes of superoscillating functions? No, it is not the only method. 3 years ago, during the COVID times, Yakir proposed another method to generate new superoscillating functions. What he was proposing is to consider a set of points in the interval -1, 1. He was proposing to construct a finite linear combination of exponentials in which the frequencies were this given set of points. And then the question was to determine the coefficients that I have denoted here by x sub j of n in such a way that the q derivative of this function fn evaluated at the origin is equal to I times a to the power q for any q from 0 to n. What does it mean? Basically, it means that these functions fn have the same derivatives at the origin as the function e to the iax. And so basically, they have the same Taylor polynomial of order n. We are prescribing the derivatives at the origin. So all the business is to compute the coefficients x sub j. Can they be determined? Yes, because basically one can write a linear system that can be uniquely solved using the van der Waals determinant. And so we have a theorem of existence and uniqueness of these coefficients. Whenever we are given a set of points in minus 1, 1, as soon as h sub j is different from h sub I, the coefficients can be uniquely determined, and they are given by this expression. And as a consequence, we have another different family of superoscillating functions, which are, again, a finite linear combination of exponentials of frequencies with frequencies bounded by 1 with these other coefficients in front. We can construct plenty of examples. For example, we can take these frequencies. You remember that earlier I was considering 1 minus 2j over n, everything to the power p. And such a sequence had the limit e to the I, a to the power p times x. Here, by construction, if I pick these frequencies, these coefficients are constructed in order to have a sequence convergent again to the function e to the iax. So this is another example of choice of frequencies in such a way the limit function is this one. So this result has been published in 2021, and it is in collaboration with the same group of people I already mentioned, plus Tomer Sushi, who is here somewhere, or he was here. And there is a follow-up paper by Bernd, Colombo, Schlosser, and Struppa. This one is recently accepted in the transaction of the AMS. And with Colombo, Struppa, and Alain Iger, we are considering some regular sampling and even some irregular sampling in the interval minus 1, 1, trying to find the answer to the big question, is analyticity in relation with the notion of superoscillations? We know that if a function is analytic, we have the superoscillations phenomena, but the converse is not true in general, and we are trying to figure out under which assumption the result becomes true. In order to do that, we are considering different types of sampling, and we have these two preprints. Well, one is already submitted, the other is almost finished. Okay, let me now move to the several variables case. So we have seen superoscillating functions in two variables already appearing in the description. What about the case of several variables? first of all, what will be a generalized Fourier sequence in several variables, and then what would be a superoscillating sequence in several variables. So assume to consider d variables in the space Rd, in the Euclidean space. We shall call generalized Fourier sequence in several variables an expression of this form. We take the product of exponentials, each of which in one of the variables with some frequencies and with some coefficients in front. Note that this time we allow the coefficients to be a complex function. So we allow complex valued coefficients. We shall say that such a sequence is superoscillating if in the limit we obtain a product of exponentials in which the new frequencies in the limit, if we start with frequencies, say, bounded by 1, the frequencies in the limit are larger than 1. An important example of generalized Fourier sequence in several variables is this one. Take our original coefficients in the prototypical superoscillating sequence. Take also the original frequencies, but take them to the power q1 when considering the variable x1, and then q2 for the variable x2, and so on and so forth. A few years ago, we proved that this function in, let's say, d plus 1 variables is just a question of what is d. Here, d is d plus 1. This generalized Fourier sequence is superoscillating when a is larger than 1 under an additional assumption, namely p, which appears here as an exponent of the frequency for the variable x, equals R1 Q1, Q1 is this, plus blah blah, RD times QD, where QD is this one. So we could prove the superoscillating behavior of such a sequence, but under this assumption. Fair enough, but of course the goal for us was to remove any additional, apparently non-necessary assumption. And it was possible to do that, and I will illustrate the case of two variables that can afterwards be generalized to the case of d variables where d is any d, even larger than 2. The starting point is a superoscillating sequence in one variable. Let's say this one, constructed as you wish. It may be the prototypical one, a variation of the prototypical one constructed in another way, but you must start with a superoscillating sequence in one variable. Now, extend from the real to the complex variable x, call it xi, and assume to have convergence in the space A1. Now we define a new sequence, a new generalized Fourier sequence, in two variables. I don't call them x1, x2, I call them x and y. How is that one formed? We keep the coefficients. We take the original frequencies to some power p for the variable x, and to some other power q for the variable y. Then, if we construct a generalized Fourier sequence in this way, in the limit, we get the product of two exponentials, where here we get a to the power p, here a to the power q. And in particular, this is superoscillating when a is in modulus larger than 1. How can this be proved? Again, we need an infinite order differential operator. Careful that we are constructing an operator which is of infinite order in the variable xi, which is like, let's say, an auxiliary variable in this discussion. This operator has non-constant coefficients, which are depending on x and y, the two variables we are considering. So our operator curly u, in this case, is this guy here, in which we have the derivative with respect to the complex variable xi. This operator acts continuously on the space A1. So how do we proceed? We start from our original generalized Fourier sequence. This is an exponential, so we rewrite the exponential by means of the series. Then we expand using Newton binomial. Here we get the frequencies to some powers, and then we observe that these powers of the frequencies can, in fact, be obtained by taking the derivative of this order of the exponential function in the variable xi, evaluated for xi equal to 0. So basically, we have to consider the operator curly u I have just introduced applied to the superoscillating sequence in one variable. And if we do that, since this operator acts continuously on the space A1, we can exchange it with the limit. We get this, and then we just have to evaluate at xi equal to 0. And if you do that, you get exactly this series expansion here. And here you may recognize the Newton expansion of this guy. And so at the end of the day, we end up with what we wanted to prove, namely that we obtain this exponential in the limit. We can do that for d variables. So the case d equal to, in reality, explains, of course, it becomes terribly more complicated, but it explains the case of d variables. We have to consider, in this case, an infinite order differential operator, which is more complicated. Here, this is not a typo. We have some functions which are going to be a little bit complicated of these variables. But in any case, it is possible to do all the computations and to show that this operator is continuous on A1. Can we do something more general? Yes. Instead of taking the powers of the frequencies, we can consider some holomorphic functions, G1, G2, Gd, instead of just considering the powers. Under suitable assumptions on the holomorphic functions, I'm not putting all the details, we can show that in the limit, we obtain this product of exponentials. In particular, this function is superoscillating when the modulus of the functions g, L, evaluated at A, is larger than 1. Now, as yesterday Fabrizio was explaining, and also Daniele, I think, mentioned this, why to consider only the exponential function? Of course, when we consider the exponential function, we can speak about frequencies, we have a certain description. But from the mathematical point of view, the phenomenon can be described also for other types of functions. The idea is you have a function, you perform a sampling in a certain bounded interval, and you get values of the function outside this interval. This is the idea. Of course, one cannot speak about superoscillations. The new notion is the notion of supershift. And we have this notion also in several variables. How it goes, assume to consider a sequence or sequences of functions, let's say bounded by 1. It can be any real number positive k0. Consider some entire holomorphic functions, g1 up to gd. We say that this sequence, which is a finite linear combination of the product of these d holomorphic functions with some coefficients in front, has the supershift property if in the limit we obtain the product of the same functions, which are now evaluated at the points x1 times a, x2 times a, and blah, blah, blah. And if a is in modulus larger than 1, we have obtained the values of the function outside the sampling interval. This is the notion of supershift. As you may understand, clearly the superoscillations are a particular case, since the exponential is a holomorphic function, but this is, as I said, a particular case. Now, this study was done in the past under the additional assumption with the usual group of people. And more recently, where we have removed the assumption, we have done the paper also in collaboration with Andrew Jordan and Tomer Shushi. Let me point out that there is another follow-up paper in collaboration with Colombo, Pinton, and Struppa, which treats the general case of supershifts. I would like also to mention that the notion of superoscillations in several variables was considered earlier in a paper by Berry and Dennis. This paper appeared in Journal of Physics A in 2009. And there is also at least one follow-up paper, this one, which is more recent. Berry is considering superoscillations in d dimensions. However, the setting is completely different. He is considering monochromatic waves. And also the problems he's treating, as far as I understand, are a little bit different. Mainly the problem he's considering is the computation of the probability that a point is in the region of superoscillation according to his definition. But anyway, I wanted to mention the existence of these papers for completeness. The discussions with Yakir have originated several works in several different directions in mathematics. I have to say that all the discussions with Yakir that has normally to repeat several times a problem before we understand. But anyway, anytime he's repeating, behind this there is some beautiful mathematics. And normally he is right. So we had the inspirations for several different directions of studies in mathematics. And surprisingly enough, if you wish, we have also some directions which go in the hypercomplex setting. I know that there are people, even here at Chapman, that used to work in Clifford algebras. This is why, before to end this talk, I wanted to mention also this possibility. So I would like to cut it short. I will consider a Clifford algebra that I denote here by R sub n. What is this object? Instead of considering only the imaginary unit I, the traditional imaginary unit of the complex numbers, imagine to consider n imaginary units. All of them have square, which equals -1, and they anti-commute among them. The algebra they generate over the real numbers is a so-called Clifford algebra. That is this object here. You can form functions from the Euclidean space Rn plus 1, where an element in the Euclidean space is written as an element in the algebra in this form. And you can consider functions of such an element with values in the algebra. The algebra has real dimension to the power 2 to the power n. These functions are analytic when they satisfy, when they are in the kernel, of the Dirac or generalized Cauchy-Riemann operator. So they satisfy this equation. Okay, since the setting is non-commutative, we don't have the traditional properties that one would expect, like this function here, the monomial x to the power m, is not analytic in this sense. Not even when m is equal 1, not even the identity function is monogenic. Of course, polynomials are not monogenic. The exponential function is not monogenic. At this point, you are asking yourself, so you can do almost nothing. No, at the opposite. One has the full treatment that one has in traditional complex analysis can be more or less restored in this framework with possibly different definitions, for example, of the product, and different tools. But one can do, for example, a Cauchy formula. One can do almost everything. Why I'm mentioning here that the exponential is not an analytic function? Because it is all the same meaningful to consider functions which are analytic in this sense and which satisfy a bound of this type. You remember when I introduced the space A1, I also mentioned the spaces AP, where I put the exponent P on the modulus of Z. Here I can do the same, but considering the space of monogenic functions. I have a notion of convergence in these spaces. And we can introduce infinite order differential operators. Under some complicated assumptions, I can form infinite order differential operators where the derivatives are with respect to the variables x1 up to xn. The variable in the real direction x0 does not appear. Here we need not the pointwise product, but a suitably defined product. But in principle, one can study infinite order differential operators in this framework, and we have results in this direction. For example, there is this paper in collaboration with Alpai, Colombo, Pinton, and Struppa, where we treated infinite order differential operator on entire holomorphic functions. But it is not the only paper that we have in this field of studies. So to conclude, let me only remind you that if you want to learn something on the mathematics of superoscillation, this is a main reference in which you can find all the basic material, although it needs to be updated because it goes back to the 2017, I think. In reality, it was written earlier. And for the basics about physics, the recommended reference is this roadmap, which contains a full list of references. And I thank you for your attention. Yes?
I'm confused, and I was wondering if you could help me. I always thought of superoscillations as being a function which oscillates nicely at low frequencies, and then in some small region, it's got these very, very fast oscillations.
Yes.
Whereas your expressions seem to tell me that these sums added up to a very high frequency everywhere in space. So I'm confused where, why the difference between the two of them, between my naive expectation and what I seem to get out of the kinds of things that you were saying.
If I get it right, it is true that the original prototypical example and the examples that arise from that one, or also the construction that I have shown, that one constructing the coefficients using the van der Monde determinant, all these sequences are superoscillating in the sense that you are describing. They fast oscillate in some regions, in some intervals.
But your expressions that you had there seem to be expressions, ax, e to the I ax oscillates fast from minus infinity to infinity. And
that is the limit function, e to the iax. That is the limit function.
Perhaps you could say, what's the sequence that approaches?
About this.
Yes, please.
You have a series that each term in this series is plus infinity, minus infinity. It doesn't exist. So you write a series of Cn e to the I kn x, sum of it. Each one of the Cn is plus infinity, minus infinity. There is no meaning to it. Nevertheless, in the sense of distribution, you can show that the sum of this Cn has a well-defined limit, which is e to the I alpha x everywhere in space, and only infinite as infinity. It's a new thing, like the Rah function also is ill-defined, but you can define it only as a limit of a series, and here you have a limit of a series that each one of the terms inside the series is plus infinity, minus infinity, plus infinity, and that, as nevertheless, the sum has a well-defined limit. The sum of the terms is not equal, the sum of the limit of the terms is not equal to the limit of the sum.
No.
The sum of the limits doesn't exist, because you have 1 plus alpha to the power n. When n goes to infinity, alpha is larger than 1, then it blows up completely. And you have an oscillating series that each term plus infinity, minus infinity, and nevertheless, you can prove that the whole sum has a well-defined limit, and that violates the Fourier theorem, because it shows now that in all finite, in all x, you can write e to the I alpha x a sum of other Fourier components, provided you are allowed to take infinite coefficients of this type. Not a normal system.
What is the physical application?
Sorry?
What is the specific physical application of physics?
No. For physics, you have to use only a finite, because that thing will mean that the probability to find the thing in real space is zero. All the probability is infinity. It's an interesting new mathematics, but not for physicists to consider only finite things. And then you don't have this problem.
Please.
And many thanks for the talk. And instead of, before Clifford algebra, I think I would be interested in functions of several non-commuting operators instead of several variables. So I wonder how the Baker-Campbell-Hausdorff formula would modify the Newton identity. Would it change the result?
We never tried that, although we were discussing recently exactly what you are suggesting. Because in the case of Clifford algebra, one does not have commutativity, but in a very special case. Whereas if one puts, for example, non-commuting operators, of course, the Hausdorff-Campbell-Baker formula needs to be applied. And we didn't do the calculations yet. But yeah, it's something to which we are talking about. If you wish, the case of the Clifford algebra, it's one of the possibilities if you are willing to increase the number of dimensions without moving to the several complex variables. So it's an alternative way.
Okay, let's